Hello. Today we're going to talk about self-adjoint operators. First, let's review some ideas from before about normal operators. Let V be a finite dimensional vector space over either the real numbers or the complex numbers, and fix an inner product on V. A linear operator T from V to itself is said to be normal if T composed with its adjoint is equal to the adjoint of T composed with T. We have a few properties here. Say that T is indeed a normal linear operator on an inner product space V. Then the norm of T of x is equal to the norm of T adjoint of x for any x in our vector space V. Given any scalar C, T minus C times the identity transformation is also a normal linear operator. Say that x is an eigenvector of our normal linear operator T having eigenvalue lambda. That is, T of x equals lambda times x. Then x is also an eigenvector of the adjoint of T, but with eigenvalue the complex conjugate of lambda. That is, T star of x equals lambda conjugate times x. And finally, say that x1 and x2 are eigenvectors of T corresponding to distinct eigenvalues lambda 1 and lambda 2. Then x1 and x2 are orthogonal to each other. We have a few more properties we'd like to state. Say that T is a linear operator on an n-dimensional inner product space V. Assume first that the characteristic polynomial of T splits over our field F. That is, the polynomial f of T factors as plus or minus 1 times T minus lambda 1 to some multiplicity m1 times T minus lambda 2 to some multiplicity m2 and so forth. Here, the lambda sub k's are eigenvalues of our field in our field F. Then there exists an orthonormal basis beta for V such that the matrix representation of T with respect to beta is an upper triangular matrix. Finally, assume that V is a vector space over the complex numbers. Then T is a normal operator if and only if there exists an orthonormal basis beta for V consisting of the eigenvectors of T. As a remark, recall that T is diagonalizable if and only if there exists a basis beta consisting of eigenvectors of T. For today, let's first go over the following motivating example. In the previous lesson, we considered the 2 by 2 matrix that you see here on your screen as a rotation counterclockwise by an angle theta. Here we're assuming that theta is a real number so that A has real entries. This matrix is normal because A times A star, the adjoint of A, equals A star times A is the 2 by 2 identity matrix. In fact, we can do a little bit better. Let's consider this matrix Q that now has complex entries. Then we have the following diagonal matrix, B, which is Q inverse AQ. We can express this so that the diagonal entries are now complex numbers. We can write them in terms of e to the I theta and e to the negative I theta. Here, e to the I theta is equal to cosine theta plus I sine theta by what's called Euler's formula. Let's actually consider a real valued example of this. Instead, let's consider the following 2 by 2 matrix A, which we'll write in terms of hyperbolic cosine and hyperbolic sine. Here, t is a real number, so that cos t and sinh t are both real numbers as well. This matrix is normal, but it is actually symmetric. That is, A is equal to A transpose, which of course is the same thing as A adjoint because the entries here are real numbers. In fact, if we write a similar matrix Q to what we had above, then we find another diagonal matrix B, Q inverse AQ, which in this case has real numbers. B here is the diagonal matrix that has entries e to the t and e to the negative t. Let's use all of this to discuss the concept of self-adjoint operators. Say that V is a finite dimensional vector space over either the real numbers or the complex numbers, and let's fix an inner product on V. A linear operator T is said to be self-adjoint or Hermitian if T equals its adjoint. As a remark, in practice, we always choose f to be the real numbers so that the self-adjoint operator really corresponds to a symmetric matrix, that is, the matrix representation with respect to beta of a transformation T. In other words, A equals A transpose. Let's write down a few properties. As before, say that T is a self-adjoint operator on an n-dimensional inner product space V. First, T is a normal linear operator. Second, every eigenvalue lambda of T is a real number. Third, the characteristic polynomial of T splits. That is, f of T is equal to plus or minus times T minus lambda 1 to some multiplicity m1 times T minus lambda 2 to a multiplicity m2, and so forth. And finally, assume that V is a vector space over the real numbers. Then T is self-adjoint if and only if there exists an orthonormal basis beta of V consisting of eigenvectors of T. You'll notice how this is related to the idea of being a normal transformation. We just said that when f equals the complex numbers, then T is normal if and only if there exists an orthonormal basis beta of V consisting of eigenvectors. Let's go ahead and prove these statements. The first statement, that is that T is normal, follows from the identity that T composed with T adjoint equals T adjoint composed T just equals the square of T because, of course, T equals its own adjoint. Now let's prove the second statement. We want to prove that all of the eigenvalues are real numbers. So for the moment, let's say that the eigenvalue lambda is a complex number, a plus bi. We need to show that b is equal to 0. Since we have an eigenvalue, that means we have an eigenvector. So there exists a non-zero vector v such that t of x equals lambda v. However, t equals its own adjoint, so t of x equals t star of x. And we've seen that because t is a normal linear operator, that t star of x equals lambda conjugate times x. Now subtracting the two sides away from each other, we see that lambda minus lambda conjugate times x must be the zero vector. But x is not the zero vector, so lambda minus lambda conjugate must be 0. This occurs if and only if lambda is a real number. Let's go ahead and show the third statement. Let's choose any orthonormal basis beta for V and consider now the self-adjoint linear operator L sub A, which is just left multiplication by A. We'll also consider the n by n matrix that's going to come from A, which will come from the linear operator T. Now, let's extend the scalars just for the moment so that instead of working over possibly the real numbers, let's work over the complex numbers. We'll show in a moment that actually really doesn't matter. We can just restrict to working over the real numbers. Since we are working over the complex numbers, we know that our characteristic polynomial splits. This is just the fundamental theorem of algebra. But now the roots of this polynomial, namely the lambda sub I, are real numbers. This is what we just showed. So this polynomial now must factor over the real numbers, not just the complex numbers. That shows the third statement. Let's go ahead and prove the fourth and final statement. We need to show an if and only if. Let's assume first that there does exist an orthonormal basis consisting of eigenvectors of T. Then we can consider now the matrix representation of T with respect to this orthonormal basis, and we find a diagonal matrix. Now, if we consider a adjoint, then we know that A adjoint must equal A because we are working with a self-adjoint operator. But now, if we consider A minus A conjugate, we then see that this is really the same thing as the matrix representation of T minus T adjoint. And of course, we find that T minus T adjoint must be 0, so that T is a self-adjoint operator. Conversely, let's assume that T is a self-adjoint operator. Then we know that we can find an orthonormal basis so that our matrix is upper triangular. This is, of course, because we know that our characteristic polynomial splits. Now, if you simply stare at the upper triangular matrix that we have, the only way that this upper triangular matrix is equal to its adjoint is if the elements away from the main diagonal are 0. That means A12, A13, and so forth must all be 0. And so we find that for each eigenvector, T of Vk equals AKK times Vk, showing that beta is indeed an orthonormal basis consisting of eigenvectors. This completes the proof of the theorem. Let's go ahead and recap some of the main ideas that we've covered over the last few lessons. Say that V is a finite dimensional vector space over either the real numbers or the complex numbers, and let's fix an inner product on V. Let T be a linear operator on this n-dimensional inner product space V. Recall that T is diagonalizable if and only if there exists a basis consisting of eigenvectors of T. Now let's assume that V is a vector space over the complex numbers. Then T is a normal linear operator if and only if there exists an orthonormal basis beta consisting of eigenvectors of T. And finally, let's say that V is a vector space over the real numbers. Then T is self-adjoint if and only if there exists an orthonormal basis consisting of eigenvectors of T. Thanks very much for watching.